talk about how to find the weak link in binaries, and Ollie Whitehouse, he's here to explain it to us. Thank you.
Thank you very much. Good afternoon, everyone. Yeah, my name's Ollie Whitehouse. I work for a company in the UK called NCC Group, but this work wasn't necessarily done at NCC. This work, to give you a bit of background, is really the culmination of several different research projects and the experience of different problems inside software development. So to give you a bit of background, up until the end of last year, I worked for Research in Motion, the people who make the BlackBerry. And so one of the challenges that we ran into was how to make security scalable. So we can all sit in this room and discuss software security because we work in the profession, but as soon as you start interacting with software developers or technical QA staff that have to test for software issues, obviously the knowledge drops off very quickly. And so the purpose of this presentation is really to explain to you how the tool is built from the ground up, but as you'll see at the end, basically it culminates in a utility or a program which can be used by pretty much anyone to identify the weak links in binaries. So to give you an idea what we're going to cover, we'll go through the what are we looking for when we're looking for these weak links, why, and then how. So again, I'm going to really delve into how we go about detecting these deficiencies or the presence of these defensive mechanisms, and then some conclusions. So when we look at what we set out to do and what was the initial goal, if we have a Windows binary which we don't have source code to or necessarily private symbols, we want to be able to gain some level of assurance that like a secure development lifecycle has been followed when writing that binary. Or alternatively, if we're a researcher, we may want to identify those binaries which are less well protected. And we want to do it easily and we want to do it quickly. So that was that's the mission statement of the project, I guess, and this is how we achieved it. So when we look at on a modern Windows operating system, and I do discuss ELF and UNIX later on in the presentation, but generally we have a number of different defenses available to software developers. So there are a number of operating system provided defenses. So the fact address-based layout randomization exists is a property of the operating system typically, and a binary has to opt in. Then there are a number of compiler-provided defenses, such as stack cookies that protect against overflows. We want to be able to detect binaries that do or do not have that property. A number of linker, and then there are some different aspects that the actual developer physically has to make changes to the code or turn features on in order to benefit from. So that gives you really a feel for how wide the subject matter is when we start looking at what these weak links are or what developers have to think about when they're writing software today. They have to cover off an awful amount. So when we start digging into what we start looking for, so we will look, for example, at the version of the compiler. And the reason that we'll do that is Microsoft's, if we take Visual Studio, for example, has gone through a number of different generations. With every generation, certain defenses have improved. So if we take, for example, stack cookies, that was introduced initially in Visual Studio 2002, or Visual Studio.NET. The implementation of stack cookies in that particular version of the compiler was easily, or relatively easily, subverted. So yes, there were stack cookies, but they weren't as robust as the Visual Studio 2005 SP1 version. So if we can accurately fingerprint the version of the compiler used to compile different modules, and we see that stack cookies are present, but we know it's from an earlier version, that gives us some hope from an attacker perspective that we may be able to successfully compromise a binary still, or from a defensive perspective, we know we have to go back and actually recompile with a modern compiler to mitigate that risk. We then have a number of specific compiler and linker-enabled protections on Windows. So these basically say, because Microsoft had the legacy problem, which has always been their Achilles heel, early versions of Windows didn't have ASLR, didn't have DEP, and so binaries had no awareness of it. So to ensure compatibility, when they started introducing these features, they took the right approach, and they said that developers have to effectively assert that my binary is compatible with these new features. And so the developer is effectively opting in to these extra defensive mechanisms. So ASLR, you don't get by default. DEP, you don't get by default. And again, as I discussed, stack cookies. And then we have the safe structured exception handling as well. The developer has to certify that their binary is compatible and is not going to crash. And then we have a number of developer-specific changes which they make. So, for example, the developer, if they wish, can say, if you detect any heap corruption, Microsoft default heap, just terminate my binary. The default behavior is to kind of soldier on and kind of keep working, and that's because there's a surprising amount of developers that suffer subtle heap corruption without any negative or apparent negative effect on their application. But Microsoft has very aggressive kind of heap integrity checking now, and if they detect that, binary can just kind of fail close, as it should. There's DEP policy, so the developer can opt their binary in to say, I'm opting into DEP, which they may have already done through the linker option, but then also say, don't ever allow it to be turned off, because a common exploit mechanism was that initially the first stage of the payload would basically opt or turn off DEP for the process and then jump to the second stage of the payload. And you can say, no, don't do that for my binary. But it's a good indicator, again, that developers have actually thought about these kind of types of attacks and put in appropriate mitigations. And then there's a whole raft of other specific defenses. So DLL planting, at a high level, DLL planting is when, for example, you navigate to a network share and you double-click on a binary and say it's for a particular extension type, if that binary doesn't have the DLL required to parse that file available or already loaded, it will actually use the network share which you're loading the remote file from as the first place it looks. So the idea is you put an attachment or a file and a malicious DLL which the user's application will then attempt to load remotely to achieve arbitrary code execution. And there was a whole raft of, well, basically most products were affected by this in one guise or another when it was first kind of identified. But there are specific mitigations that developers can use to stop their applications being targetable by that type of attack. And again, we can detect that, and again, it gives us kind of a confidence factor on whether or not they knew what they were doing. And then there's other kind of more performance impacting options like pointer encoding. So there are facilities available in the OS through a standard API to actually encode long-lived pointers in memory to protect against overwrites or info leaks and similar. We then have a whole raft of other things. So Microsoft's SDL, Secure Development Lifecycle, they have 145 APIs that are banned. We can obviously detect for the presence and the use of those. Again, it's a pretty good indicator, strong indicator on whether or not it's kind of been band-aid patched to make it more secure versus actually being thought about from the start. There are a number of dangerous APIs, and I'll go into specifically what those are and how they undermine security. But again, they're not documented by Microsoft, but as a kind of a sneak peek, use of one of the APIs effectively allows a developer to inadvertently undermine the use of ASLR on Windows if they use it incorrectly, and we'll discuss that. Then the UAC, the obnoxious user experience that Microsoft introduced with Vista, that has the concept of integrity levels, and we can enumerate that. And then there are some .NET specific features. So that kind of gives you an overview of, there's an awful lot now. If you say, is my Windows program secure? I've just spent, 6 minutes discussing all of the different things that we're going to have to check for to be able to answer that question effectively. Doing that in a manual way, repeatably, reliably, and without having kind of the knowledge we have in this room is both time-consuming and boring, right? So how do we actually do it on a repeatable basis? And why first? So this is a great example. Adobe gets, a lot of bad press at the moment, unfortunately, because they are, the vector of choice, although Oracle may be soon there with Java. So Adobe writes Reader 10, which is one product. The number of vendors that actually have software shipping in the Adobe Reader installation package is actually about 8 or 9 different software vendors contribute different libraries and different components to the Adobe product. So while Adobe will be making positive noises about how they're improving their secure development lifecycle, et cetera, the same is not necessarily true for the supplier upstream that's kind of Jane and Bob and their dog. It's 3 people and a goat writing code that contributes to the Adobe Reader. So how do we gain assurance of all of those suppliers? When you don't have source, you don't necessarily have private symbols. And this is pretty much, this echoes the problem that we suffered at RIM, right? Where there were certain products and we wanted to gain assurance of it. There was also some other benefit. If you're an end user organization and you're deploying these software products, you want to understand how secure they are, because if they're insecure, you can start looking to use technologies such as EMET. So for those that aren't familiar, what EMET is quite a clever bit of technology from Microsoft that you can take a program that hasn't necessarily been developed in a secure way, doesn't opt into technologies like ASLR, doesn't have mitigations against exploitation, and really kind of like cram a massive band-aid around it to force some of these protections on and kind of throw in some other mitigations into the mix that wouldn't otherwise be available. So although you're running, some crusty piece of software from the beginning of the last decade, the fact that you're running it on Windows means you can use EMET effectively to kind of bolster its security posture. So end user organizations being able to understand where they need to deploy that is obviously extremely useful. And so to give you an idea, prior to NCC, I wrote a small tool that would enumerate your program files directory and literally spit out an EMET configuration file for every binary on the machine that didn't have the appropriate protections. So you could literally just import that into EMET and literally raise the kind of the security level of all of the previously unprotected apps instantaneously with relatively little effort. So this kind of echoes the point. Adobe's SDL may not flow upstream. If you are a vendor and you ship code, you want to make sure that it's not RSA that's going to kind of burn your security reputation. And as I mentioned earlier, end user organizations, I don't think we're at a stage yet where all vendors can be trusted. So most of the mature end user organizations we're working with, at least, want to have some visibility and take ownership of that risk and then put in appropriate mitigations. If you flip sides and go away from defensive onto offensive, kind of a lot of the same messages are but in reverse. So undermining ASLR or finding the info leaks to ASLR, kind of working out how to bypass stack cookies in a particular exploit or the particular heap implementation, that's all expensive, right? That doesn't come for free. That's your time investigating how to kind of develop those techniques. As we get to more and more defenses being present, we spend more and more time doing application-specific exploitation techniques rather than kind of lean on the A key, get EIP, everyone goes to the pub. So we want to maximize, if our end goal is exploitation, we want to make it, that we spend our time researching those products which we know are going to be relatively trivial to ultimately exploit if we find a bug. And this kind of echoes that a little bit. I appreciate that Chris and Ryan didn't necessarily set out to fully exploit, or they may have, they may not have, but they didn't achieve it. So post to full disclosure, I guess early last year, there was a reported denial of service in the IIS FTP daemon. So Chris and Ryan, it basically disproved that and demonstrated that it was controllable memory corruption, where they achieved control of the instruction pointer, but they couldn't get arbitrary code execution because of the presence of ASLR. They did not simply know where the binary was to ROP into, and there were no kind of RWX pages, and they couldn't spray effectively. So they've done all of that work, but they still actually haven't achieved their potential end goal. And that's effectively what we want to minimize when we do this analysis. So if we dig into how we do it now, so what I'm going to do is literally walk through every mitigation and then how we detect for it without source or symbols. So the version of the compiler linker, the link is very easy. So you'll see these tables extracts on a lot of my slides. What those are parts of the Microsoft P binary or COF binary specification, public specification which you can download and read yourself. So the version of the linker is stamped in, which is relatively easy. What's more interesting and not documented, by Microsoft at least, is this rich header. So at the top of every Windows binary, there is this, it starts with the rich magic, and then there's an XOR encoded blob. In that XOR encoded blob, there is the compiler version ID of every compiler used to compile every object that went into that end executable. So these are nondescript numbers, and it's been known about on the internet for a long time. So 2004, kind of the virus Ezine 29A picked it up, and then it was further documented in 2008. So this kind of gives you an idea of how trivial it is to decode that in some just C#. So found this, and then January 2010, went through a mapping exercise. Because these nondescript numbers, you don't know that that is Visual Studio X or Visual Studio Y. So we went through, and as a kind of a social group, went through and mapped every version of Visual Studio at every service pack level to be able to map these kind of arbitrary IDs to particular compiler versions. And so why do we care? Again, because it goes back to one of the earlier points. Firstly, that kind of stack cookies have improved. Local variable reordering didn't come in quite late on the Microsoft compiler versions. And then there was also certain compiler versions that these mitigations weren't present at all. And you'd be surprised to find, you'll be surprised to hear the number of times that you see the outer binary is compiled with Visual Studio 2008, but there is an object inside of it that has been compiled with Visual Studio 6. So while the outer binary has been compiled with like the latest and greatest or the near latest and greatest, there is still some legacy compiled binary object also present, which is useful, again, for if we're targeting particular functions or particular functionality. ASLR is extremely trivial to detect. It's stamped into the P header. Again, kind of opting into DEP is stamped in, so these are all relatively trivial. What I would say is the best thing Microsoft have ever done is when they released effectively a .NET wrapper P parser written in a managed .NET wrapper. So they've done a lot of the heavy lifting for parsing the P headers. Originally, I wrote it in C version 1. That didn't support 64-bit. I then tried to use Microsoft C version, which did 32-bit and 64-bit, and that didn't always work and crashed, and found a C# version, which lifts a lot of the heavy work for us. A point about DEP as well, and I got burnt by this, is on 64-bit, even though it may say that the binary is not opted in, it doesn't matter. The OS always turns it on. Because I noticed, for example, EMET, the 64-bit DLL, doesn't actually have this flag set, but it actually has no impact. Stack cookies, there are 3 ways that I use to detect them. So one is there is this security cookie header field, which isn't always populated, but it is one tell that we can use. If you have a debugger build, you can actually look at the import table and see if the CRT debugger hook is present, which is another possible mechanism of detection. And then the heuristics approach. So the heuristics stuff I originally, presented back in 2007 while at Symantec. It's effectively a really cheap way for us to fingerprint the prologues and the epilogues of the stack cookie implementations for the different versions. So again, it gives us resolution in terms of saying, yes, there is stack cookies used within this binary, but between the very early, or the first few versions at least, it also gives us function resolution. So we can say, yes, it is stack cookie protected, and it's protected by Microsoft Visual Studio 2003's version of stack cookies. So again, we kind of get that fine-grained detail if we need it. Safe SEH, we only have to worry about it on 32-bit. It's stamped in the P header, and literally you'll see these header fields. So again, it's pretty self-explanatory when you kind of start digging in. This was quite an interesting bug. So the first bug of this last year. So load a configuration directory. If the size is wrong, basically it opts out of safe SEH, which is a very kind of a weird anomaly more than anything else. It was a bug in the Windows loader. The problem is that the Visual Studio or Visual C runtime from 2003 RTM has the wrong size. So any binary compiled with this early version of Visual Studio will literally have a big chunk of DLL that you can jump to using like a safe SEH overwrite without tripping over safe SEH, or using an SEH overwrite without tripping over safe SEH. So we can, again, kind of flag binaries. So a good example here of a binary that does suffer this is PuTTY, the SSH client. is compiled with this older version and is vulnerable to this bug. So we then start getting into some other kind of less well-known aspects, I guess. So in the PE file, there is the default process heap flags, which I've never seen be anything but kind of read-write. But in theory, it could be read-write-execute by default across the process. So as a result, we can again flag binaries that are misconfigured in that way. We have the shared section problem. So these would be mapped across different instances of the same process, across potentially different users. So we will flag, for example, those that are read-write or execute read-write and shouldn't be. And then, as I mentioned earlier, there's a number of defensive APIs. So the way that we do it is the developer calls heap set information, and they specifically pass the parameter terminate on heap corruption, and as I mentioned earlier as well, enabling dep forever. So if developers are calling these, we know that they're probably on top of their game and, at least from an attacking perspective, step away. And then the SDL APIs, as I said, 145 of them, and we can do that relatively quickly. So this is a good example of one of those APIs which Microsoft doesn't document the behavior of, but yet undermines some of these defensive mechanisms. So if a developer uses virtual lock, it will not be opted into ASLR. If you use virtual lock directly, rather than malloc or similar, you don't benefit from ASLR. And you'll be surprised the number of developers that directly call virtual lock and then with read-write-execute. Google obviously knew about this bug, because if you look at the Chrome source, they've written kind of a pseudo wrapper where they try and kind of add some entropy to the addresses which are returned by virtual lock. But they actually have a bug in their implementation, which is as you kind of get over kind of the initial allocation, so say the first 100 meg or 200 meg, the amount of entropy drops off significantly. So I guess would have been at the beginning of this year, where I was working somewhere else, we released a secure version of virtual lock called virtuallock_s, which uses an algorithm where it tries to do top-down, bottom-up randomization and some other stuff to try and increase it. So it's something to be aware of. And you'd be surprised that when I was testing this, I guess, against products, Office, Adobe, again, were vendors that had used virtual lock directly, mapped pages, read, write, and execute. So, it gives us a target point for our exploitation. As I mentioned, load library is the root cause of the DLL planting problem. So again, kind of analyzing that. So these are the mitigations, effectively. So what we check is, does the binary use load library create process? Yes, it does. So it's potentially dangerous or it's potentially vulnerable. But then we check that does it not also then use these other 3 API calls? Because those are the new APIs, the newish APIs that Microsoft introduced that would mitigate DLL planting. And there's also some other ways via the registry that we can mitigate these vulnerabilities, which I'll discuss in detail in a slide or so. The UAC integrity level is easily retrievable from the binaries manifest. So for those that aren't familiar, Windows binaries, they have code in. They can also have resources. So, for example, graphics, icons, et cetera, These are stored in, effectively, resource sections. One of those resource sections is simply this well-defined XML, which effectively will instructs Windows to whether or not to pop up that dialog saying, I need to elevate, do you authorize me? So we'll check the level that it needs to and whether it wants UI access. UI access is very dangerous and very rarely used, thankfully. It is able to see that secure grayed out desktop. So if a binary has UI access, which is granted, whenever the UAC prompt comes up, that actually is generated from a secure desktop, and you're not meant to be able to programmatically interact with that dialog, because otherwise you could just authorize everything that wanted to elevate. So if it does have that set to true, it can interact with that dialog and click it through. So something to be mindful of. And then there's some .NET security elements. So strong name checks, allowed partially trusted callers. Most of the .NET code I see don't really use these, and they're not anything significantly to write home about. But if you are kind of in a very hostile environment, I guess, you'd want to at least understand whether or not these features had been used. More interestingly, for .NET assemblies, is we want to check whether or not it has unmanaged code in. So it is possible in .NET, although it is a managed language, to effectively undermine .NET in its managed nature and have your own buffers and actually lead to memory corruption. Again, it's kind of a rare, that is relatively rare to do, kind of actually make terrible, horrendous mistakes like that. But again, we can identify at least if the binary is interesting to us, to, for example, memory corruption vulnerabilities by the presence of unmanaged code. We then also wanted to start detecting, so Windows 8 was in preview, I guess, at the time, doing this work. And Windows 8, for those of you that aren't familiar, has very kind of similar model to the Android capabilities model. So there is like a capability called access to pictures or similar. And those all run within these kind of new defined sandboxes, which are far more restrictive than the kind of UAC model. And so I was interested initially on kind of how it knows that it's a Windows 8 binary that should run in a sandbox versus just be a kind of a standard Windows binary. So effectively in the DLL characteristic, which is part of the PE header, it effectively says I'm a Windows 8 binary and I should be sandboxed. And then actually in the manifest, which is the same manifest that we get the UAC data from, then lists the specific capabilities that the binary actually needs to function. So again, we can enumerate those pretty easy. And if you want to kind of read the work I've done on that, or at least documenting, there's a blog post there. Force integrity is one of those interesting properties which, again, is rarely used. So what force integrity says, so Windows has this strange behavior. If a binary is signed and the data and the signatures don't match, Windows will treat it as unsigned and continue to load, which is, relatively strange, but you can understand why they did it to, a little bit of corruption never hurt anyone or something, So, but they introduced this flag called force integrity, which says, effectively, if there is any difference between the signatures, then refuse to load. And the only time you actually see this in the crypto libraries, generally. But again, we can kind of detect for its presence and flag. And then we pull out some other information, and this is more useful to researchers than it is to vendors. But we pull out, for example, like company name, file version, who signed it, and the signature type. And what you'll see sometimes is a significant disparity between who wrote the code and then who signed the code. And so you do have to wonder, these vendors that are just signing arbitrary binaries from arbitrary sources, whether or not they actually do any due diligence. So anyway, questions, not answers. So what I'm going to cover now is, I hate repeating other people's work just for the sake of it. I'm not one of those people that wants to make a better wheel for the sake of it. So I try and avoid that where at all possible. So I thought I'd go through and recognize and appreciate the work that others had done in this field and why I still kind of continue to battle on. So Looking Glass came out, I guess, in about 2003, was a .NET-based PE scanner, and it looked for things like the bad SDL API usage, and a couple of other things like, was it ASLR enabled, was it DEP enabled? But it was quite minimal in its checks, and they obviously didn't develop it any further. But it was a good start, and it was relatively interesting as a concept. Microsoft then came out with BinScope, and BinScope is awesome if you have the source code or you have the private symbols to a binary. But it didn't solve kind of the itch I had. So they do a lot of what I've discussed, but they don't do it all by any means. But also by virtue of the fact that they have the debug symbols, they can actually do some things that at the moment I've not worked out a way to do without those symbols. So for example, they can check whether or not the global stack cookie variable is actually initialized properly. Because I guess they've seen examples where the stack cookie actually isn't initialized to a random value, which would be horrendous, if you could catch those. And they've obviously worked out a way, they can obviously do that because they have private symbols, but we don't, because we don't know where that variable is necessarily. And then also, by virtue of the fact that they have private symbols, they can check the ATL versions in use. So there were a number of, there was at least one vulnerable version, and they can pull that out and flag. But as I said, you know, the negative is you need private symbols, which aren't always available. So basically, now we're going to kind of discuss or show how I did it. So just to show that there's nothing up my sleeves. So we're going to run it on Adobe. Oops. I always pick on Adobe because they were normally at the top, if I can actually find them. So it's nothing particular against Adobe. So it's just running a quick scan now. You'll see it's relatively quick what it does. I would dance at this point if I could, but I can't. So while it's running, effectively what we see is the path, the file name, whether or not it parsed it correctly. Is it a 32-bit or 64-bit version? And then we can see the compiler versions that I discussed. So what we can see here is, you know, Visual Studio 2005, SP1, yeah, that's all good. So the fact that it's red must mean that there is an earlier version somewhere along the line. So why is that flagging? Great, can't see why. But there must be a Visual Studio 6 somewhere along the line there. So we get the compiler versions out, whether or not we need to worry about them. And again, what we can see here is whether or not they don't use SCH, and if they do, whether or not it uses safe SCH, does it use NX, ASLR, stack cookies, the UAC integrity level. And you can see here that this really embodies what I was saying around trying to make tools easy to use so you don't have to be an expert. This was designed to be used by software testers. So they could literally run this on the end build, and they would understand green is good and red is bad, right? So let me just find the vendor I'm looking for. So we can see here, RSA at the moment. So we can see, like, this is a great example. So Adobe is signing software from Right Hemisphere, Environmental Systems, IBM. You know, whether or not they have the source code to all of this, I don't know. But we see at the bottom RSA, that well-known trusted security company. And we see that actually they're the worst, apparently, on the actual use of a lot of these kind of proactive compiler defenses. And I do appreciate that the fact it may be an old version of the library, but it's actually in use by a product vendor, right? So this kind of gives you an idea on how we use such a tool for targeting. But then we can go through and we can see, you know, virtual lock is used more than you would think it should be. As you can see, force integrity is typically negative, et cetera, et cetera, et cetera. So you get the idea, and we can click on any of these and, you know, view the banned API usage that they're doing, et cetera. So you can see it's, you know, it's relatively accessible. Okay, so that's it for the demo. If we move beyond the binaries, we then also have to start looking in the registry if we want to deploy some of these defenses, or we want to check for their existence. So there are three in the image execution options registry key. There you then create a subkey, which is the name of the binary, and then there are three. So CW DLL legal in DLL search mitigates DLL planting. Mitigation options can be used to force address space layout randomization on for binaries that don't typically opt in. And then we have safe SCH overwrite protection, which is another SCH defensive mechanism which can be opted in as well on desktop, on by default, on server. So that's kind of like, that shows you how hard it is, basically, and what you need to think about. I wouldn't say hard, but there are lots to think about if you're trying to defend binaries. But even with all of these, there is still a very prevalent kind of type of code construct that can lead to easy instruction pointer overwrites, which we still haven't mitigated. And it's simply this, and you can refer to the slides. But if you take this example and compile it even with a new version of Visual Studio and supply in lots of A's, on the command line and press enter, you will achieve an EIP overwrite simply via a kind of a C++ vtable overwrite. And I'm very surprised that we have yet to mitigate this class of issue at a compiler level with cookies or something similar. But anyway, something to bear in mind. So if we move on to, so yes, my world has been Windows for a long time, but I was very fortunate at RIM to spend some time working on QNX and then looking at some of the problems there as well. So there is a similar tool from trapkit.de for analyzing ELF binaries. So it checks, for example, is the ELF binary using dangerous APIs? Does it opt into, is it like configured, compiled with position-independent execution? So does it use ASLR and similar other things? But there was this interesting property of ELF binaries that I wasn't aware of, and I contributed the patch back into checksec, which is in an ELF file, you can have in one of the sections called rpath or run path named literally a file system path. And that file system path can be absolute or relative. And interestingly, that overrides any loader options. So like LD preload we all know about. So if you had a SUID binary, for example, that referenced a path which you could control or create, it provides a way of injecting libraries into binaries that you wouldn't otherwise be able to if you couldn't write as root to the shared library directory. So I released the checksec update went out with the patches in, and then someone told me afterwards that Ubuntu did quite a big patch afterwards because there were quite a surprising number of binaries, again, that were using runpath or rpath. So something to bear in mind anyway when analyzing Unixy binaries. So yeah, I guess what I'm trying to say from all of this is I've kind of documented the thought process, the reasoning, and how it was built, but it doesn't have to be rocket science, right? We don't have to make tools that require a PhD in rocket science to actually use. I think they can help significantly with the kind of assurance and assessment work that we may do, either as an end-user organization, consultants, researchers, whatever. And then obviously if you are an attacker, it can help with target identification and where to spend your pennies without the use of symbols. What I would say is it's not done right. Microsoft keep innovating, and we're always playing catch-up. So the /SDL switch that was introduced in the latest version of Visual Studio introduces something like 7 new protections, which are all very subtle, and they need kind of detecting now as well. So it never finishes. Okay. So that's it pretty much for me. Are there any questions? One question. Thank you, Chris.
How can we get access to the tool?
Just email me, and I was trying to make my millions by selling it, and I've realized that wasn't going to happen because no one buys security tools. So just email me, and I'll throw a copy over. You already have employees with a copy anyway. But,
okay.
Any other questions? Okay, well, no, he was just he already has a copy. If you have any questions afterwards, obviously feel free to email me and I'll happily answer them. Slides will be available instantaneously. And as I said, if you want a copy of the tool, ping us and we'll get you one. So thank you very much for your attention. Have a great day.